Hello. Hey, Mike.
Hey, can you hear me okay?
Yeah, can you hear me?
Yeah.
All right. What's new?
Well, that about brings you up to speed.
Okay. Oh, thanks.
I'll take questions. No, I won't actually. The usual, just depressed.
Oh, hopefully this meeting will help.
Well, the social anxiety that comes along with it. My original intention was just to leave the camera and microphone off the whole time, but
Oh, okay.
then I saw you there alone.
Cool.
If I was smart, I would do just one push-up
Yeah, there you go. You had the idea.
or
That's a start.
create just one method.
Yeah, yeah. Then you'd be small talking.
It's tough putting breakpoints in the parser because a lot of the mechanism does a lot of parsing.
Uh huh.
It's the usual systems level stuff.
If you just go one step, that's a lot of work.
Well, it's not just the work. It's a lot of the, I'm in VisualWorks, but a lot of the tools, they might just call the parser, the debugger might just invoke the parser to format the code or do the colorizing or something,
Mm-hmm.
It's like, I don't need colorized source to debug, but,
Mm-hmm.
So my workaround is I do like conditional based upon the process that I'm doing, and then I'll just fork my code off, and so it only halts if it's a particular process.
Mm-hmm.
That's my trick.
Yeah.
What you been up to?
Oh, I've been writing a parser actually.
That sounds familiar.
Yeah.
Um, you're using some parser generator tools.
I wrote a new one.
Oh, cool.
Yeah. Yeah, we
What
had a couple
style?
of things we wanted to parse, and we have the EBNF rules for them. And I tried a couple of other frameworks and just found them too hard to debug. Um, so I came up with something where the production rules themselves are reified uh, objects, and they hold on to all the state they encountered during parsing. So they actually, when the parse is done, they serve as the parse tree and the parser and the compiler. And you can use individual rules as search terms when you want to search other rules for parts of their structure or parts of results or terminals. And that last thing has turned out to be the biggest uh, advantage of this approach.
Cool. Yeah, I think you might have mentioned it at the last meeting.
Yeah, I think I did. I've been working on it for several months. Actually, I
Yeah, I
did it.
meant to ask you, did you try it out on a Smalltalk grammar?
I want to do that next. Yeah, so far
Cool.
we've used it on protocol buffers and SVG, which is mostly XML, and had good success with both of those. So I think it can handle anything for which you have either the actual EBNF or railroad diagrams, or at least a good prose description from which you can derive that.
Mm-hmm.
So yeah, it would be fun to
Oh, it's
throw it
fun.
at the classic railroad diagrams from the Blue Book.
I was watching Gilad Brock on one of his YouTubes where he's talking about Newspeak and how he did parsers in Newspeak so that as such you could actually, with one of its you could have inner classes as grammar elements, but then you could specialize them within the language, specialize as like subclass them. So like just for instance, you have like a small talk literal that works across all small talks, but then you could specialize it for like Squeak's got its dynamic array syntax, which looks like gemstones but completely different. The curly brace.
Right.
So it was a cool approach towards parsing, particularly if you've got like families of similar but different languages. It was a nice approach to not having to have like a separate grammar for similar languages. It was cool talk.
Yeah. So I guess we'll officially get started in about 3 minutes, 10 past. I'm going to go grab a cup of coffee.
Okay. Let's see who else we got here.
Has anyone else spoken yet?
Not yet.
Okay. This could be a quiet meeting.
like I could give a lightning talk on what I wish I was motivated to do.
Yeah, excellent.
So, do you ever do like virtual pair programming?
Yeah.
You know, where you share a screen with someone and you pair with them?
Uh-huh.
Yeah, I always like that. And so I had this idea that would be kind of cool. You divided the display into three different sections where one of like the left section, I could do whatever I want, but you'd only see it. The middle section we could both interact with, and the right one, you'd have it's sort of like, you'd have right access to it, or view only versus click through. And so you could kind of like do your own thing, isolate from the other one. You got like little parts working. You could bring them into the middle section where it's shared. I haven't quite, figured out whether you'd have like separate images or that of course gives you the most isolation. But
Cool. Yeah.
okay, just a cool little idea for social programming.
Mm-hmm. Oh, here's Dave.
Is on.
Hey, Dave.
Hey, how are you?
Good.
Looks like we have a light turnout tonight.
Yeah.
Said there was only about 10 people who were planning on showing up. So.
Mm-hmm. Oh, yeah. 13. Oh, 14. Yep, one person's already left.
Okay, well, there you go.
14 what?
14 people signed up, and 5 people have been in the room so far, but 1 left.
Yeah, no,
Yeah. What you been working on, Dave?
I am working towards a paper for managed languages conference, the CFP's mid-May, and so I'm working on a new Smalltalk environment, virtual machine, basically.
Cool.
Yeah, with a different dispatch model. So that's so semantically the same, but different implementation of that. So that's what I've been working on, and I've been I was working on it in Rust, which is a pretty good language, but I've come across a language called Zig, and that's what I'm using, what I'm working with now. So it's a pretty interesting language, actually. I don't know whether you looked at it at all, but it has first-class types. It's a statically typed. So Rust is sort of a C++ replacement, but Zig is actually more of a C replacement, which is actually what I need more.
Yeah.
So, but it has first-class types, which turns in not quite like Idris does, but it makes for an interesting language. So that's coming up to speed on Zig is used part of my cycles, and it's also the end of the semester, so I have an exam coming up in a couple of weeks, so I have to prepare for that. So not my favorite thing.
Yeah.
What have you been doing?
Oh, I've been writing a parser compiler thing that is easier to debug. It's easier to debug itself, and it's easier to debug grammars that you're trying to parse with it. It uses eBNF, and it reifies the production rules. and
Okay.
makes them do the parsing, and makes them also act as parse trees when the parsing's done.
Hmm.
And you can use rules to do searches within the parse results of other rules.
Okay.
Speaking of parse trees, I was playing around with John Dugan's macros for VisualWorks. I don't know if you ever saw that.
No.
He was basically doing it for Lisp Envy.
Mm-hmm.
In fact, I've actually used this package more than he did. He just like did it. It's a fairly small but intrusive mod to the compiler. He had a nice little interface to it. You used a backtick. So you do a backtick message send
Mm-hmm.
Syntactically. And during, like the way there's the parse tree expansion for like the open coded structures like if then,
Mm-hmm.
it occurs at the same time, same mechanism. When it sees that backtick message send, it sends that message without the backtick to the parse node, and whatever returns, it splices in right there.
Ah, okay.
So, the very simplest one would be like quote, backtick quote, which
Mm-hmm.
basically just returns the original parse tree. So if I did like put some block of code and then said backtick quote, then I would get a literal block node, the syntax element there.
Hmm. That's fun.
Hmm. Looks like we may be it. Oh,
Oh, hello. We can't hear you.
Oh,
Oh, there's something.
can you hear me?
Yeah, heard that.
Okay. So I'm sorry, I was having dinner and I connected, but wasn't listening. So I want to say hi and thank you for organizing these meetups, even
Sure.
if we are for this time.
Yeah.
And well, I'm here to learn from the masters. I'm just beginning to exercise some things in Smalltalk. I'm taking a course on object-oriented design, and that's it. I'm
Cool.
following the MOOC, the Faro MOOC alongside, and trying quiz because the class I am attending is well, they are very very engaged with quiz. Hernán Wilkinson and Máximo Prieto here in Argentina.
yeah.
Cool. Yeah, welcome.
So just taking my first baby steps, hoping to learn from the masters.
Yeah. Well,
Cool.
yeah. Smalltalk can be a bit deceptive because the language is so tiny. As they say, it can be done on a postcard, but the class library is so large that coming to understand how to leverage that well can take a while.
Yes, and it can be shocking for someone without prior experience.
Mm-hmm.
I use Emacs every day, and I kind of like this idea of having this ability to introspect and inspect everything. But Smalltalk takes that to another level completely.
Yeah, absolutely.
Mm-hmm.
And well, just a couple of minutes before Hernan Wilkinson was giving this like a short talk about the Smalltalk meta class model, and my brain melted because there were so many arrows pointing everywhere.
Oh
But
yeah.
in the end, the idea is it is simple. It is just what is needed to achieve a result in this very simple model of sending messages to objects
Mm-hmm.
and nothing else. So it feels like it was a long day. I remembered Zig too. The guy that the main maintainer of Zig is working on it since
Andrew Kelly?
quite a. I played with it a little just to have a taste, but I never use it for serious stuff. I remember he did a great music player before working on Zig. Nice guy.
I was just gonna, when you mentioned the class stuff, I don't know if I can do this, but let's try this. Let's select a window if I can.
Yeah, that part of Smalltalk can evoke a lot of strong opinions in the Smalltalk community.
Mm-hmm.
Like what?
Well, different Smalltalks, may or may not have this depending on where you are in their timeline. But there's this, at least in the older Smalltalks, there's this, you'd expect the method new to be on the class side of object, because you send new to a class, and it gives you a new instance of that class. But if you look, it's not there. And figuring out why it's not there and how it still works leads you to something, I think they called it the prime anomaly. That was sort of like a rite of passage for understanding how the meta system works.
Mm-hmm.
Yeah, well, I am quite sure I won't remember anything I saw today, but now I have I am encouraged to go and explore by myself and learn.
Well, if you want to understand that part, the Blue Book has a pretty good write-up, complete with diagrams with lots of different kinds of arrows. It's probably the best, short of having a person, it seems to be the best.
Yes, but I mean I have the system running live on my computer, so it's like a conversation. Well, you can have a conversation with a book too.
Mm-hmm.
It's just an idea.
Hey, Giselle.
Well,
I'll be right back.
Okay. What's new?
I got a little bit confused about the schedule because of the daylight saving times.
Oh, yeah.
Guess I won't have to worry about that anymore.
Hope not. Maybe one more time. That would be good.
Hopefully they'll leave it this way until we all go to star dates.
Until what?
Until we all use star dates.
Oh yeah, star dates, right.
Yeah, here in Brazil, they stopped that about 2 years ago. So it's been 2 years without daylight saving times. But
Hmm. So you're on standard time now?
yeah, I think that.
Yeah, yeah. You're permanently fallen back. No more moving forward.
Yeah.
Yeah, we moved forward, and they want to stay there, but I'd rather be back.
A couple of years ago, for my social calendar, I tried using the French Republican calendar.
Is
Oh yeah.
It was kind of fun, and 10 months, 10 days of the week, go metric system.
Yeah, nice. 10 hours, 10 minutes, or 100 minutes maybe.
Yeah.
Or maybe not even have hours anymore, just 1,000 minutes or something.
I can't. They did decimalize the time. I can't remember exactly how they did it, but at least the metric system part of it stuck.
Yeah.
I thought I'd share screen just for a second for
Yeah.
this deal. So let's try allow. So does that look familiar?
Oh, right.
Yeah.
I have to. Yeah, so this is a lecture from the beginning of my course of int to. Can you see the? I'm not sure what you're seeing exactly. So
Yeah, we're seeing you scroll back to only small integers.
yeah. Okay.
Oh, I think I have to look refresh my screen because I am not seeing anything.
So now you added integer to it.
Yeah. So
Okay.
looking at superclass,
Mm-hmm.
and then all the way up to superclass of proto object. So is it Ezekiel here, or is he? Can you see this, Ezekiel?
Oh, he's re-entering.
Okay.
By a strange coincidence, yesterday I was watching Alan Kay talk that he gave at Park Place. Yoshiki recently posted it, and he was saying how much he hated meta classes.
Oh,
So anyway, I'll just quickly go through this. So then you ask for what's the class of one, you get small integer class, and this is the category theory that all connects to each other properly, and
Right.
we get all the classes all the way up. And then what if we ask for another class? Well, then we get a meta class. And what's its class? Well, it's a meta class. And back we go. So anyway, I just thought, because you were mentioning it, that I would share the
Oh, that's
Yeah.
great.
class.
Thank you. At least the arrows are straight, not so curvy. That's nice. Thank you.
Actually, there's a up to version 3 of the. That's a little bit more astronomical.
yeah.
So where did you start? Oh, you started with undefined object.
Undefined object. That's
Tried
like
to
the
make
Big
it
Bang.
lay it out a little prettier by putting class undefined object at the center.
Yeah.
Right. So the difference between version 3 of Little Smalltalk and version 4 is that version 4 is like this. Well, version 3 still had the Smalltalk 76 scheme, where all classes were a subclass of class, which meant you couldn't have class methods. You only had instance methods. The only
Yes. From what I heard, that was a requirement by because when they tried Smalltalk with the children of all ages, they ask for this feature to be able to use class messages easily and to create objects that way, instances. Well, that's what I heard.
I'll be back in a minute.
Okay.
Yeah, the Smalltalk that they experimented with children was a Smalltalk 72, and Smalltalk 72. That actually got me really interested when the Byte 1981, August 1981 issue came out with about Smalltalk. They claimed that they had taught it to children. And I read all the articles and I didn't understand it and said, whoa, I can't understand something that children learn easily. So, and that was a little bit misleading because that's what they were describing in the magazine was not what the children had played with. So there's a little bit of difference between Smalltalk 72 and Smalltalk 76 and 80. But
you want to hear a sad story about that? I came across a tiny little article pre the Byte magazine about the Smalltalk, just a tiny little write-up, Smalltalk at Park and that. And I remember reading it, and they talked about how it was a programming language for kids. And, I was just kind of a kid myself. And I remember as I read it, it's like, yeah, I don't want kid stuff, and just passed it over and didn't cross Smalltalk. Smalltalk didn't really cross my path again until like the early 90s, like 1990. And then when I realized, I was like, oh my God, my prejudice against it being a kid's language, I fell in love with Smalltalk then. And it's like, oh, I missed a whole decade of doing the coolest language ever.
Well, not a whole decade. I mean, when was the earliest you'd be able to get your hands on Smalltalk?
I don't know. I was kind of like enamored by Lisp, and I remember writing a quick little Lisp interpreter. So, but yeah, it's not like we had the internet back then. That would have been tough.
Yeah, the first time I actually ran a little bit of Smalltalk code was when I got my hands on Methods, which was the first Digitalk product before Smalltalk V. It was a text mode Smalltalk running on the PC. This was 85. So at the end of 85, I had been interested in Smalltalk since 81. I really wanted it. But the only way that I was going to get it was if I wrote a version myself, which I worked on a little bit. Mm-hmm. So that's a problem. Just knowing about it, we had a lot of that problem with Self as well, because it only ran on Sun Spark workstations, which people didn't have. So you could give the coolest demo, and then the person would go back to their PC and it didn't run there. So what was the point? When it eventually ran on the machines that people had, then nobody was interested anymore. All the interest had died down. But so when people were excited about it, they couldn't get it. That happened a lot with Smalltalk as well. I mean, Methods and then Smalltalk V were very usable, even on PC. But the Park Place things were Sun workstations and up as well, so they were out of reach financially as well. So you'd have cost $3,000 or something like that to get. In fact, one thing that really hurt Smalltalk was when they merged Digitalk and Park Place. and they removed all the cheap products from the market. So you could, the previous year you could buy a $49 Smalltalk for your PC, and now suddenly you couldn't anymore. The entry level was $3,000.
Yeah, well, I started VisualWorks on a Macintosh, and it's great that it was on like a more consumer class machine, but the software price, still basically killed you. But fortunately, powerful computers are aplenty, as are free Smalltalks.
Yes.
Yeah, I mean, a very early Smalltalk was the little Smalltalk that I was talking about, although it was the version 1 was very different. But yeah, it didn't have, it still doesn't have a GUI, so it's a command line Smalltalk. GNU Smalltalk was like that. I don't know if it has a GUI these days.
It had a GUI way back. It was called Blocks or Block, something like that, I think.
It depends on.
It didn't work very well.
Back.
Well, like in the 90s, like 94.
Really?
Yeah.
Interesting. The first good Smalltalk that I got my hands on was called Smalltalk X.
Yeah.
And originally it started as a little program that would translate Smalltalk to C. So you'd write your little Smalltalk program, and then it spit out a C program that then you compiled with a C tool. A little bit like later we had slang or whatever, and then to make it more interactive, he added a bytecode thing, and then an interpreter, and then eventually a whole GUI in all the traditional Smalltalk languages. So by the time I got to it, was this 94? Trying to remember. But it ran really well. I had to expand my computer. I had a 4 megabyte Linux computer, that's 386. And I had to expand it to 12 megabytes in order to be able to run Smalltalk in X11. I mean, X11 was more of a memory hog than Smalltalk was. But what was amazing about Smalltalk X was that it was so fast that it was easier for me if I wanted to edit a little text. It was actually faster for me to boot into Smalltalk X, use its built-in editor, like we have the in the workspace you can edit. So I called the file thing and edit and use the text pane to edit the contents of the file. Then to open up a terminal and call VI or whatever. I mean, no, VI was faster, sorry, but there were the graphical alternatives like JOT, J-O-T, and so on, which were programs written in C, and they were slower than Smalltalk X for compiling. So I was very impressed, and that's still available to this day.
Yeah.
And it was mixed, so you could get it for free, but there was also the commercial version. So they had some clients that paid.
Yeah.
So it was open source at the time. I don't know if it ever became open source, but yeah, it's amazing. The alternatives that we have now. I mean, just Squeak split into 3. So you have Hero, Squeak, and GUIs to choose from. So
I'll bet Craig has at least 3 of his own Squeak lines.
Well, Caffeine at this point is sort of its own beast. Yeah.
Spoon?
I guess it includes that. Yeah. The module system and all the live web support. But yeah, it's not really changing anything fundamental, just optional stuff.
I remember for a while I was trying to collect all of the different small talks I could, run them all at the same time, and then take an expression and see what expressions would evaluate the same in every language.
Mhm.
You know, you have to use like the fairest syntax and.
Mm-hmm.
Yeah, around the year 2000, a lot of people didn't have good internet connections yet. So, for example, there was a guy from South Africa that wanted to watch the structure interpretation of computer programs. SICP is talking about Lisp. It's a great computer science course based on Lisp, and they
And
had
available freely online, I'll point out.
what? Sorry.
And the book's available completely freely online.
Yes, it is available, and they had put the videos for the 1986 edition of the course, where they gave it at HP instead of at MIT. So and they put it online, you know, those MPEG-2 files or whatever, and I was able to download it, but the guy from South Africa wasn't. So I created DVDs and CDs and whatever, and shipped them by snail mail to him. So I saw that, and there were these great online materials for Smalltalk, but I thought, yeah, maybe a lot of people are in the same situation. So I wrote to everybody that was responsible for free stuff and asked them for permission for me to create a CD-ROM that, you know, you'd get it and you'd get everything that you normally download. So I got the two great Smalltalk archives back then were at the University of Illinois, and Mario Wolsko had created one at the University of Manchester with a ton of Smalltalk material. Adele Goldberg had something that she had created for the Open University, I think, that was a learning system implemented in Smalltalk. There was Smalltalk X, there was Squeak, there was, I'm trying to remember all the ones, including Self or whatever. So I wanted to make it as easy as possible. So as soon as you put it on your disk, if I loaded Squeak, a tiny little Squeak image, there was a menu for the CD-ROM, and then you could jump into any of the Smalltalks from Squeak, then come back to the menu or whatever. So the problem I had was I could call random programs from Squeak in Macintosh in Windows, but the version that the last official version for Linux couldn't do that. And Ewan Pio Martha had was this Squeak 2.7? I'm trying to remember what version it was. It was something like Squeak 2.7. So I was waiting for the Ian to release the official Linux version of Squeak 2.7, so that I could use that, and then you know you'd run it in Windows, Macintosh, or Linux, and then you'd have all the menu and stuff. And he ended up never. That was a version that was never officially released. So that version of Squeak was only officially released for the Mac and Windows, and never for Linux. Jumped to the next version, and so I got distracted with other stuff. And I really, the other day I was looking for that CD-ROM because I had to create a few local copies, and I can't find anything. It's not in my backups. Don't know what happened to it, but it was a great snapshot of what Smalltalk was like in the year 2000. And I wasn't hoping to make a lot of money out of that. I was going to charge a minimal thing. It's just, to me, it had the PR value. So, to just make people aware of the various Smalltalk options that were available. But I still, the emails from the people authorizing me to, so I explained that, it was I was going to make a little bit of money, but it wasn't a for-profit project really. So trying to remember, but anyway, I have the emails from all these people allowing me to use their free stuff in that way, because a lot of people were weird in that they distributed stuff for free, but you could only get it from them. You couldn't get from a second person. So if somebody downloaded that, this was before BitTorrents and stuff. But so, for example, Netscape, you can get it from them directly, but you can't get it from a friend. It was illegal for you to get it from a friend, for example, that had already downloaded and passed you a copy. So since people were kind of weird in that sense, I said, let me guarantee by getting everybody's written permission that they're allowing me to use that material.
So I have a question. I was having some trouble reading some metacello files in Quiz, and I think it was because of the encoding. I solved the problem by recoding the files, but maybe why is that? Why do they use different line feed conventions? It's something because is it because of the Macintosh?
Probably.
Yeah.
I think the Macintosh line-in convention actually came from Smalltalk.
Oh, well, that makes a lot of sense.
Interesting.
So I had to use the recode command. I have to first read the metacello files in Faro and do a file out, and then use the recode command to be able to load them in Quiz Smalltalk. I know there is a way to change the line feed convention in Quiz.
Yeah, you have several dimensions, unfortunately. So besides the line feed carriage return stuff, and you also have it can be UTF-8, or it can be Mac Roman, or it can be. So there's lots of ways to mess things up. I mean,
in addition, you could have multiple classes for the internal implementation of a string.
Yes, it's kind of so surprising. It works. It works most of the time.
Yeah, we had.
I worked at a place that did the internationalization for VisualWorks, so I know far more about Unicode than I ever wanted to.
When the very first Squeak came out, it actually had some methods where it just was returned a string, which was the C code for a little piece of the system. And we had problems that you'd spit that out. So there was a command that would save that as a file so that you could C compiler. and not all C compilers would like it because of the line ending. So you get into trouble because of that. You go into that squeak mess and say, oh, save all the C files, and then create it. Just write that string to the disk, and that would have the Macintosh line endings, and then try to compile with GCC, and it says, oh, this is not a C file. I still every time I use the Linux tools to deal with files generated from Squeak, I always have to start with the tr command, replace the slash in.
Yep. Yeah.
So I actually found out that I was having more trouble, more problems than that, because sometimes there are some weird characters, and then grep will quit. So I create this like 4 gigabyte file with all my emails that are saved from Squeak. And then I do grep to see if I ever received an email from you. And then it says, no. Grep says, but it quit in the middle because it decided that it was a binary file rather than a text file, and it couldn't handle that anymore. So now I do more than just replace the line endings. I also strip the character above 127
Mm-hmm.
or trying to feed it to the Linux tools. And these things weren't clearly designed. They were patched and patched and patched and patched until we got to where we are. So sometimes you look at something, it doesn't make sense. And, well, every little step of it made sense. Just the end result where we got doesn't make as much sense.
Mm-hmm.
Well, some of those historic artifacts in computing can last a long time.
The left arrow.
I'm sure you guys remember the I'm sure you guys remember the underscore assignment days of Squeak.
Yeah. That was.
I immediately made a font that just had the left arrow instead of underscore.
Yeah.
I wonder if kids today even know what a carriage is.
Or an underscore.
Well, I think we still got those.
Yeah, the problem goes back to 1963. So they defined a standard for ASCII, and then in 1967 they finalized the standard and made a few patches, except that Xerox and DEC and some other companies had already implemented it in a ton of equipment.
Mm-hmm.
So they kept using it, and I think that the people working at these companies weren't aware that they weren't using the official ASCII. They were using a broken ASCII. So I imagine that if they had been aware, they would have done something a little bit different, but they weren't. So the people at Xerox PARC were proud that they had moved from their weird internal font to ASCII, and then they were using the underscore as a left arrow. Because that's how it was in 1963. And it's interesting that the IBM PC had a left arrow in its character set, although there was no way to type it. So they could have used that for methods. But the idea for methods was to that most programmers already knew how to program in Pascal. So they weren't going to teach Smalltalk from scratch. They were going to teach a Pascal programmer to move over to Smalltalk to read their manuals. That's very clear. So they decided to use the colon equals, since that's what the Pascal people were aware of. So that's where the colon equals come from methods instead of the left arrow. And it's kind of funny, man. You get programmers these days, they weren't aware that at one point C was completely unknown and Pascal ruled the world. So there was a company that actually got away. So I worked for a PC clone company in 1985, and they asked me to decompile an operating system called QNX because they were selling it as if they had written it here in Brazil. They changed the name to Analix. They were selling it, and because they couldn't actually, the laws were kind of weird back then, so they couldn't actually legally import QNX and resell it. So they had to claim that they had written it. But the government didn't believe it. So the government sent them a team of 5 university professors to check if they actually write it. So a friend of mine, he had a book called The Tiny C Compiler. In the back cover, it had a floppy disk with the source code. So he just took that out, put it in the computer, and then scrolled the listing for the C compiler on the screen. And none of the specialists, none of the professors knew C. They couldn't say that that wasn't the operating system. None of them thought to ask them to compile it in front of them and see if what resulted. So they went back to the government and said, well, we're not convinced, but we couldn't prove that they didn't write it. Because they were all Pascal programmers. Nobody knew how to program C. Everybody only knew how to program Pascal. This was 1984. Yeah.
Hmm.
So
Yeah, well, I was required to learn Pascal at high school. That was mid 90s.
was it a good Pascal at least, like Turbo Pascal?
Turbo Pascal, yes, we use Turbo Pascal. Nice IDE.
Yeah, that was good. That's pretty good. Had some improvements as well.
So
But,
I'm sorry, but I have to leave now. It was great to meet you all, and take
Yeah.
care.
Take
Bye
care.
bye.
Mhm.
recently, I've discovered that some of David Unger's old projects, he had published papers, and at the time I wasn't aware, so I was reading his papers. He had a language called Cors, Korz.
Huh.
So it has about 2 papers about that. I had no idea. I had watched a talk he gave about it, so I was aware of the talk,
Hmm.
but I had never seen any written material. And previously, he had an older project called Klein, which is self-written in self.
Hmm.
And I had looked at the code, but I had never seen any talk or papers, and I found a talk. And I actually was surprised that it's supposed to run on the bare metal. I thought it ran on Solaris or something like that. It was supposed to run.
Oh.
It was like squeaking OS. I had no idea.
Hmm.
When I tried looking at the sources, I got lost because some of the code was handwritten and some was generated, but it was all mixed together. So I spent an afternoon looking at code, and then, oh, this code is generated from this other code, so I'm wasting my time. It's sort of like studying the C code for the Squeak VM instead of the Slang, which generates it. So
Yeah.
so I didn't realize that it was supposed to run on bare metal to be a self in OS.
Hmm.
And then did I find papers about it? No, I think just a talk, but it was interesting.
Well, that makes sense. Dave worked on the SOAR, the Smalltalk on a Risk.
Yeah.
Oh, I forgot about that.
So he certainly has that bare metal vibe.
Hmm.
Yeah. I actually use that a lot in my talks when I talk about Smalltalk hardware. Recently, they renamed it as RISC-3. So instead of SOAR, and the following one was called SPUR, S-P-U-R, like Elliot's memory system as well.
Mhm.
And SPUR was also a variation of the RISC-1, RISC-2, except that it was optimized for Lisp, so it had tagged memory, stuff like that. And it was
Mhm.
optimized for multiprocessors, so it's really easy to put a bunch of processors and connect them on the board.
Hmm.
So they have now renamed that as RISC-4, so that the current one becomes RISC-5.
That's right. Risk 5 has Smalltalk in its heritage.
Not really. It actually looks like the Stanford processors. It looks like MIPS.
Yeah,
And,
no, not technically. It's more just like naming
Yeah.
and funding sort of the history.
Yeah, one thing that was inherited from Smalltalk on the RISC was when they did Spark, which was the same style as the RISC-1, RISC-2. So when they built Smalltalk on the RISC, then they decided to test its performance because David Patterson was really big on this quantitative approach. Don't do what you feel it's nice, measure it, and then exclusively correct yourself. So if you thought this was good, then you measure it, it's not good, then throw it away. So what they did was they modified their compilers to not use features from the processor. So they said, oh, what if we didn't have these tagged instructions? Oh, what if we didn't have overlapping windows? Oh, what if we didn't have that? So that's what they would do. The self group, David Unger's students did this as well. So you disable features, compile all your benchmarks, run your benchmarks, and then see how much worth it is. And then that tells you what features you want. So the Smalltalk on the RISC, it had one bit in the instruction where if that was on, then the instructions were tagged. And if it was off, then you dealt with raw 32-bit integers, right? So each instruction, for example, you could have a tagged add or a raw add, tagged load and store, and so on. And they did the measurements, and only the tagged add made any difference. The other instructions are so rare, subtract, exclusive or, are so rare that having a tagged version of them really didn't help that much. So when they designed the when they designed the Spark, they decided to add a special tagged add instruction. And for symmetry, even though David Unger had proved that the tag subtract didn't do anything, they have tagged subtract. So it's T A add T sub instructions. And what it does is it looks at the bottom 2 bits of the 32. And if they're both zero, then it'll add and subtract. And if either of them has a bit that's different than zero, either argument, it'll trap. Now, the problem with this is that the way that the Spark was done before version 9, the 64-bit version, and the way that Solaris implemented it, if you trapped, you would take almost 1,000 clock cycles to handle that trap and then return to your code. So every time you had a tagged add, it wasn't, for example, if you were trying to add a point to a rectangle or something like that. Well, you want to trap as quickly as possible and call the general send plus code. And here you have 1,000 clock cycles every time. So in the end, Self and Smalltalk running on Spark nobody ever used these instructions. They were so costly. So it was you just add a little test. So you do an and between the two guys test, and then branch this way or that way. So so when Urs also tested this, he concluded that it was a bad idea. It wasn't a bad idea. It was badly implemented. If they could have handled the case where it weren't two integers in a few clock cycles, it would have been great, but that's not what it did. In fact, he also concluded the same thing about register windows, because whenever you have an overflow or underflow, so hardware has a fixed number of register windows. So every time you overflow or underflow, then you also trap, and then you have thousands of clock cycles to fetch a new frame from the back. So he also concluded that the register windows were a bad idea, and they weren't a bad idea. They got Spark to
Yeah, I was
design.
disappointed when Sparks got rid of the trapping overflow arithmetic thing. I didn't quite understand how much, whether that actually gave any performance, especially on modern pipeline processors.
No, it doesn't help. The problem is that since people are now designing C processors rather than generic processors, anything that you can't do in C, they throw away. So C doesn't detect overflows, so I have an overflow bit that's not tested. And they, in the RISC-V manual, they show how you can have like 5 little instructions that will then detect overflow if you need it. So it's not worth having that hardware if these 5 instructions do the same job. And another thing that they don't have is rotation. So you have shift left and shift right, but you don't rotate because there's no way to rotate in C except with a very complex expression. Where you rotate left by n, you rotate right by 32 minus n, and then you perform whatever. GCC can actually translate that complex expression into a single rotate instruction if your processor has it. But other C compilers will compile that always into a bunch of other instructions. So RISC-V doesn't have rotate. No recent processor has rotated instructions because it doesn't need it. So now we're living in a C world.
Yeah. Somebody has music playing, which is the music is nice, but it's really distorting everybody's speech.
Oh, yeah. Sorry, my neighbors are playing that.
Oh, I see. Okay. There's no problem. I mean, apart from distorting the speech, it wasn't a problem. Yeah, I was actually talking about.
Can you repeat everything? Can you repeat everything you said now?
I was talking about managed languages in my course today, and one of the things I was mentioning was the Spark architecture that had the tag for integers, and also the Burroughs 7700 was a really interesting architecture. Probably predates most of you, but it was in the 60s and early 70s.
My first computer was the Burroughs 6700.
Okay, so the 7700 was basically an algol machine. So it was, it had, so you programmed in, I don't remember what it was called, but it was a systems programming language that was algol based. That
Yeah, ESPOL, ESPOL, right?
But the 7700 actually had hardware tags for the types of things, so that I don't remember what the word size was, but it was.
It was 48 bits plus 3 bits of tag.
Yeah, the normal programs can access the tags, but the privileged software could.
Yeah, it had 51 bits in all.
Yeah.
The 6700 had a panel where it had a little lamp for each bit on the top few words of the stack.
Yeah.
So as your program ran, it was a room-sized panel full of LEDs that blinked. And what it would do is, once in a while, if it had an emergency, a crash or something, it would write a bunch of bits to the stack such that
Right.
you'd see a message like halt or something like that. And that was cute. Well, I never got to see that. I worked with this machine a lot, but so Alan Kay likes to talk a lot about that because the designer of that was one of his professors at Utah.
Okay.
David Barton. David Barton. Oh, is it David or Richard Barton?
Bob.
No, sorry, David Barton.
Bob Barton.
Bob Barton. Bob Barton. Yeah. Sorry about that. I'm really bad with names, but so
I had a TA at Berkeley whose name was Dave Barton, and he was my favorite instructor ever. Anywhere.
Any
I wonder if they're
relation?
related. I don't know. I didn't think about that till now.
So that was the Burroughs. Actually, that's a little bit older. It was introduced a few months before I was born, in 1961. The Burroughs 5000. So for the Burroughs 5000 had just one bit of tag. So a word could be protected or not protected. And then for the 5500, which was the follow-on model, they added the bits to detect if it was floating point or characters or pointers or whatever. And that allowed them to reduce the instruction, which was previously, I think, 12 bits or something. They were able to reduce it to 8 bits because now you only had to have one add instruction. You didn't have to say add what, because the tag bits told you what to do. So they were able to reduce it, and that was Alan Kay was really a fan of that. So that inspired Dan Ingalls to design the byte codes for the Smalltalk 76. So Smalltalk 76 is basically a software implementation of the Burroughs thing. They stopped making these machines a while ago, but you can buy from them a virtual machine that runs on a x86 machines, physical x86 machines. I think it's called Series A or something like that. It's from Unisys, right? Because Burroughs got merged with what is it? Univac?
Well,
Yeah, Univac. Yeah.
But the company was called Remington Rand.
Unisys after it got merged. Yeah.
But they became Unisys
well,
anyway.
now that we're entering the world of soft cores, maybe we'll start seeing some revival of some of these older tagged architectures. Who knows?
Oh, it could be.
I have seen a couple of papers of people trying to add tag bits to a RISC-V.
Yeah, well, actually, I'm part of the group that's trying to design that. So there's an extension called the J extension. So I don't know if everybody here is familiar with RISC-V. You have a very basic instruction set, and then you have a bunch of extensions, and you can create your own extensions if you want. And there's the whole set of instructions of how to do that, but you can use these standard. So, for example, multiplication is not part of the instruction set, but then you can include the M extension, and then it has multiply and divide integer. And floating point is not a part, but if you add the F extension, then you have 32-bit floating point. The D extension, you have 64-bit floating point. The Q extension, 128-bit floating point, and so on. V for vector instructions, so on. And the J would be for Java, JavaScript, those kind of languages. So we've been meeting for what, 2 years now, more than 2 years. And initially the focus was on how to deal with adaptive compilation, JIT compilers running on multiprocessors. So maybe you compile your code on one processor and then another code will try to run it. But their instruction caches could be out of sync and that would mess things up. So the first year, the focus was on that. And then somebody got excited that the ARM people created something called the TBI, top byte ignore. So you could ignore the top 8 bits of your 64-bit address. So no matter what you put in those 8 bits, then the hardware will filter them out. And so you could use those top bits for a tag. That's what the original Mac OS did, because the 68,000 only had 24 physical address bits, even though it had 32 bits internally. So it didn't have pins, so they decided to put all kinds of tag bits there. And then they got into trouble when they tried to move to 68020. So they did the math, and to get in trouble for 64 bits is going to take us decades, if not a century or more. So they did the math and said, yeah, well, we can ignore the top bit. And then Intel did the same thing. And then AMD did the same thing in a way incompatible with Intel. So for the x86, there are 2 equivalents of the top byte ignore. So then the RISC-V guys said, oh, let's do that as well. But let's be fancy. So they want to have 2 registers, one which is a mask. And so you take your pointer and you mask it with this register. And then with the result, you do an OR with a base. So you can replace any number of bits with some other bits. And but then that's a little bit messy, because do you do that? If you do that for all pointers, then your address space becomes really weird. And so that's like the last year or so been focusing on that. And then, do we do that for just user mode or the supervisor mode, or I really kind of lost interest, because it seems to me to be a lot of effort for very little result. So they have some use cases, and the use cases are, there's a scheme where every time you do a malloc, it will fill with a different tag. So if you're trying to use a pointer that to a region that has been deallocated and reallocated since, you'll be able to detect that. That's one use case that they want. Another use case is for debugging. They have a scheme. I forgot what the name of the scheme is, but anyway, they want to implement that. So that's the current proposal for the J extension. Now, there are some people trying to implement tags outside this. So there's a group at, oh no, I forgot the name of the university. It's a university in England that created an extension. So instead of 64-bit pointers, they wanted 128-bit pointers, where you'd have the base and the offset and whatever. So that's called Cherry, CHERI. And they did it originally for MIPS. So they created the MIPS that had these extensions, and then your C program can use them or not, and your operating system can. They were able to patch BSD to actually make use of that, so you can have extra security. So you have what we call capability based.
They were trying to do a capability systems, weren't they?
Yes, it's what we call capability-based system. Yes.
Yep.
Exactly. So the capability system is sort of an evolution of the Burroughs thing. So the Burroughs thing is 80% the capability system. It's not complete, so there's stuff that you can do in the Burroughs that capability system should not allow, but it's pretty close. So then the Cherry guys decided, now this RISC-V thing is becoming popular, so they created a RISC-V version of that. They created an ARM version of that, and ARM actually has manufactured a chip. So there is one experimental ARM chip that you can buy that has the Cherry in it. And we'll do the capability stuff. And then they also have proposed an extension for the x86, but I don't think anybody has done that. So there's that, and there was another university that did a different thing, but they added the tags, but they hadn't decided what they were going to do with it. They just threw in the hardware so that you could have these tags. And but they didn't want to have. So you have your chip in your board, but you want to buy off-the-shelf memory things, right? Now, one trick that you could use is you have 64-bit little boards and you have 72-bit little boards that are for the error checking and correction. So instead of using error checking and correction, you could use the extra bits for tags, and that would be one solution. But people don't want to do that, so they have a scheme where they store the bulk of the words in one region of memory, in the tags in another region of memory. So, and then the memory controller in the chip will bring them together inside the chip and split them so you can use normal little memory boards. So I'm not sure that the Cherry people do that. I know that this other group is called Low Risk. People were doing that, so they had tagged caches inside the chip, but then the tags would be written separately in memory so that you wouldn't have to buy special little memory boards or whatever. So we'll see, but so there are people, wanting that.
So I've been in the Smalltalk system that I'm building. I'm using IEEE floating point tagging. Like Firefox does. I don't know whether Chrome-based browsers use it as well or not, but the idea is that NANs, there's a world of NANs.
Yes.
53,
NAND boxing.
2 to the 53 NAND values in the floating point encoding. They could have done it differently. It would have been really nice if they'd made the bottom of the address space and the top of the address space be integers or be the NANDs, because then you could encode integers there and life would be really simple. But
yeah, for the Burroughs didn't have integers, but it defined the floating point such that if the value fit into an integer, it effectively was an integer.
Right. Yeah.
So exactly your idea is what the Burroughs did. So it didn't separate integers and floating point, but the floating point was essentially a mantissa with the.
Yeah. So I'm using the NAND values and then the top 3 bits of the mantissa basically to encode what type it is. So I've got so I have symbols. True, false, nil, characters, and small ints and pointers, all encoded in the NANDs. So it gives me 49-bit integers, and which, for all intents and purposes, nobody's, except where you're doing, I don't know, cryptography or something, you're not going to need more than 49-bit integers. So that's good. And
you stole bits from the mantissa?
yeah, it's a mantissa. So basically, in IEEE floating point, if all of the exponent bits are 1, then it's a NAND. And so you've got all the mantissa bits plus the sign bit actually available.
Oh, you mean when you're doing NAND boxing, not as an ordinary float.
Sorry?
So you mean you steal the bits from the mantissa when you're boxed inside of a NAND, the NAND payload?
Yes.
Oh, okay. VisualWorks, when they went to 64 bits, they implemented a new immediate for doubles by stealing 3 bits from the exponent for the tag. So small doubles, they have the full precision of doubles, but they lose the high and low end of the range from the exponents, but people don't use that as much. So, and then it overflows to a boxed object double, just similar to the way that small integers overflow
Why would
to
they do that?
integers. Or,
Why wouldn't they just, like, if they're going to have 64-bit numbers, why wouldn't they just leave the doubles alone? Because then, anyway. So because
the doubles are all.
I mean, you can when you do NAND coding, you can have either pointers or integers or doubles basically be natural, and then the others accessed by shifts and adds and so on and so forth. But the right way to do it, as far as I can see, is that you leave the doubles alone, because otherwise, if you have to shift to extract them, you have the problem of moving between integer registers and floating point registers. Whereas if you keep the doubles as natural encoding, then you can just load them directly into the floating point registers. So I don't understand why anybody would do anything different, frankly.
Yeah, actually, Elliot Miranda, I think, has a discussion about that, because NAND boxing was suggested when he was redesigning this Squeak, the Spur manager.
Yeah.
But he ended up doing, let's see here. Yeah. Let me post a link to Clement's post about that. It has more information than Elliot has, actually. Let me put it on the chat here. Here you don't find a discussion. It just explains what the format that was adopted and why it is, but doesn't talk about NAND encoding or stuff like that. But
yeah,
you can see towards a little bit after the middle, it shows that you do have to shift and do that to extract the floating point from this format. So you do have a little bit of overhead. But somewhere I'd have to look it up, but Elliot rejected NAND boxing, but yeah.
Yeah, I was just looking at that paper. In the 64-bit version of that paper, he talks about the small floating format as well.
So,
like in the middle.
Yeah, you currently have processors that, in theory they have 64-bit pointers, but in practice they're 48-bit pointers. So hardware that does more than 48 bits of addressing, I don't know too many processors that do that. Most 64-bit processors don't do 64-bit addresses. So NAND boxing is a great way to do that. With NANDs, you have signaling and non-signaling NAND, right? I think it's a sign bit. Is it the sign bit that distinguishes them? I don't remember.
No, it's the high bit mantissa.
Okay.
No, and in fact, I think it only applies to the positive ones, and I ignore the positive nans because I don't think it basically simplifies my encoding if I don't worry about that. And so I have the positive and negative integers all up at the high end. So that works out pretty well. But thanks for the post to Clements. The link to Clements' post.
You know, when this was 2014. Wow. I'm losing track of time. So
yeah, I think they made the wrong decision, because if you have to mess around with the doubles at all, you have to do the work in the integer registers, and then you have to get them over to the floating point registers. Why would you do that? You know, for the things that you want in the integer registers, those are the things you should mess around with. But anyway. But,
yeah, no,
Well, I think the basic idea is you don't have to allocate an object every time you do floating point arithmetic.
Sorry?
I think the basic idea is you don't want to have to allocate an object.
What they're doing is, yes, that's the idea of NAND coding, but or NAND boxing, but that's
this isn't NAND boxing. This
Sorry?
paper doesn't do NAND boxing.
yes, exactly.
No, exactly, it doesn't.
Why not?
Which is stupid. Like, if you're going to encode the stuff in the floating point or in the 64-bit thing, why wouldn't you? Because you want to have the double precision, why wouldn't you use NAND boxing? I mean, it doesn't make any sense.
Now you have to remember that since Squeak originally had only boxed 64-bit floating points,
right.
And so if you wanted to do something that wasn't abysmally slow, you'd had to create float vectors or float arrays. Sorry, float arrays.
Yeah.
So and then so you'd have an array of floating points, and then you could add whatever. And that was fast because then they were not boxed; they were raw, but they were 32 bits then. So we didn't have 64-bit.
You move to 64-bit architectures. NAND boxing is the only reasonable thing to do, as far as I can see. I mean, I don't want to be too snarky about it, but anything else.
Well, I suppose it'd be interesting seeing. I suppose it'd be interesting seeing a NAND boxed version of the Squeak VM. See how it performs.
Yeah, what I was going to say is that given this history, if you benchmark any Squeak code, you'd come to the conclusion that floating point performance doesn't matter.
Right.
So, and then the design was based on that. Okay, so none of our benchmarks show floating point to be important, so let's give priority to the to characters. What are the immediate characters, in small integers, and
Small float.
Well, small float's irrelevant too, I would say, on this modern architecture.
I'm just saying what's in the paper for immediates.
Okay, yeah, so you have pointers, yes, pointers, small integer, character, and small floats. Whereas
Really?
Small float, you end up losing 3 bits.
Off the exponent.
Yeah. So I mean, they obviously have different priorities than I do, but I mean, I have booleans, characters, nil, symbols, integer, small ints, and I don't know whether I said characters, but and doubles, double floating point, and those end pointers, of course, and those are all encoded in NAND boxing. So it's.
So can you decode a NAND box to a direct pointer, or?
Yeah, you shift left 15 bits and then shift right 15 bits, and you got it.
Okay, well, well, I'm not really a VM guy, so it would be interesting for someone who is a VM guy, try this stuff and see what kind. Of course, different code will give you different performance characteristics.
Yep.
Yeah, I'm still hung up on the trapping small integer arithmetic. If I was like a VM guy, I'd try to modify the JIT so I could not test for over or underflow and then run some benchmark code to see what kind of speed difference I get.
Yeah. Well, I mean, I think the original intention of having things like that was that you get some performance advantage because you wouldn't have to have software, multiple instructions to test it. But in fact, it boils down to that's in the noise, and having an extra set of registering an extra amount of cache or a larger register set is a much bigger win. So
Yeah, and you have to keep track of how technology changes. So sometimes decisions that make sense, like you said, go step by step.
Yeah.
So in
I
1990,
think a lot of these decisions were made before we had pipelining.
Yep.
So in ECOOP 95, Urs Hozo and another student, try to remember, Jan Vitek, I think. I'm trying to remember. I have to look it up. But they studied a bunch of message dispatch techniques, and then supposed that you had three different processors: a processor that executed one instruction per clock cycle, one that could execute two instructions per clock cycle, and so on. So they decided to see what the different message dispatch techniques. So one that was very good for simple processors might lose to another one that was initially bad. For example, one that has extra tests. But if you have a processor that runs multiple instructions in parallel, maybe it can execute these tests in parallel and you don't lose any clock cycles. Now you still waste memory though, because then every time. So that's a little bit the difference between an interpreter and a compiler. So if you have this complex thing, for example, testing a tag or whatever in an interpreter, that happens in exactly one point in your code. So that's only a performance problem. But if you're compiling, then every memory access is going to translate into, for example, if you need 5 little instructions to test if there's small integers or not, or whatever, you're going to have that little sequence of 5 instructions everywhere your compiled code accesses anything, any instance variable or whatever. So that's not only a performance problem, it's also a space problem because your code becomes pretty fat with all these things. An interpreter, you only do it once, so how much?
And then with space problem, with caches, space problems turn into performance problems.
Yeah, they do. Yes. In fact, in the 1995 paper was Urs Hozo, where he tested these object-oriented hardware features and decided that they weren't adding anything. The only thing that made a difference in his benchmarks was the size of the instruction cache. So larger instruction cache made things go faster. The register windows didn't help. The tagged instructions didn't help. A bunch of things didn't help. I don't agree with him. Otherwise, I wouldn't have continued to design object-oriented processors. But I saw his point. I understood his arguments. But his main argument was he looked at the output of his compiler, and then he compared it with the output for the equivalent benchmark running in C, the output of the C compiler, and they were the same. So he says, oh, really, the reason why these object-oriented hardware seemed to make a difference was because we had such bad compilers in the 80s. Now that we have these good compilers in the 90s, then the difference has gone away. The hardware doesn't help anymore. And I don't agree because it's a sort of a circular thinking. He took a processor, Spark, that was designed to run C. Then he made his code run as fast as he could. And then he looked at it and it looked like C. Well, what do you expect? The processor was designed to look like C. If he took some APL computer and tried to make it run as fast as possible, then his compiled output would probably look like APL, or Forth or whatever. Of course, you're going to get something. The output of his compiler is going to look like C because that's the.
Well, I know
that hardware.
I know I'm cribbing LNK here, but back in the early history of computers, when recursion was just some obscure CS professor's trick that no one ever really used all that much, processors didn't have stacks. I mean, why wouldn't you just support this weird recursion thing? No one uses it. So I think he's got that riff in the early history of Smalltalk.
Yeah, Fortran didn't have recursion initially, at least several early versions of it. It did when running on the burrows, though, but that was outside the standard. So there's no standard.
Well, I know the world disagrees with you, Giuseppe. I'm happy someone still stands up for high-level language processor architecture features. So, yay!
Oh yeah, but I have to be careful of another term that Alan Kay coined, which he calls reverse vandalism. So reverse vandalism is to do something just because you can. So I can write my own compiler, so I'll write my own compiler. Maybe I should step back and think, no, maybe I should use somebody else's compiler and so on. So I have to be careful not to get carried away, not to do the stuff that looks good and is not measured to be good, like David Patterson quantitative approach. So it's very tempting to do stuff just because you can. So.
Well, I can't write a compiler, so I don't have to worry about that.
Yeah, no, in fact, my current processor won't run without a compiler. A compiler is part of the design. So I've been calling it Silicon Squeak 5 to have continuity with the previous designs, but actually it's not very similar to Silicon Squeaks 0 through 5, through 4. It's a bit different. So now I'm aiming for really high performance, trying to compete with the highest performance Apple, Intel, AMD processors, while still using less energy, stuff like that. There's a very interesting group that has a similar objective. It's called, they used to be called out-of-the-box computing, and now they've renamed themselves to mill computing because their project is called Mill, M-I-L-L. And they actually worked on the Burroughs machines.
Nice Babbage appeal.
Huh?
But that it's got Charles Babbage appeal. I think he called his processor unit the mill.
Yes, it is a homage to Babbage, to his analytical engine that had the memory and the mill. I forgot the memory. What was the memory called? Memory is the von Neumann term.
It might have been the store. I'm not sure.
Yeah, probably. So, and the processor was the mill, so they named that. So they originally, at least some of the group was Burroughs, where they wrote compilers, the algo compilers for the Burroughs stuff. Then in the 90s, they worked at Philips, where they came up with an interesting processor called the Trimedia. And I actually wanted to use it in my project. So Trimedia was a very long instruction word processor. And I wanted to use it, but they kept the format of the instruction secret. I said, well, I'm writing my compiler, so could you please tell me what the instructions look like so I can write my compiler? They said, no, we don't want you to write your compiler. You use our C compiler. And so I gave up using that processor because they wouldn't give me the details. It was secret. Since then, somebody has reverse engineered and it's been published on the internet. So at least now I know what it looked like. And then starting with the early 2000s, came up with this idea where they went to go a little bit beyond the very large instruction word processors. So it's a very interesting thing, and they were keeping secret. They were going very slowly. They didn't have any financing, so it was kind of like a hobby project. And then the law in the United States for patents changed from first to invent to first to file. So the previous law in the United States, if you could prove, if somebody files for a patent, and 2 years later you come along and you prove that you actually had invented that a year before them, they'll take away the guy's patent and give it to you. But that's really hard, and the rest of the world is first to
Well, that's
file.
depressing.
Yeah, so the rest of the world is first to file. So to align them, the U.S. Patent Office changed the law. I don't know when was this, 2010? I don't remember it. Not that long ago, they changed it to first to file. So now the very first person to file for the patent gets it, and then if somebody else proves that they invented it earlier, unless they can prove that the person who filed the patent actually knew that and patented it in bad faith, then that's different. But if you proved, nobody knew, but I have this notarized sketchbook where I have this invention, whatever. So now that didn't work anymore. So they decided to stop their project, take out as many patents as they could. And then once the patents were very far along, they decided that, now we can talk about it. There's no reason to keep it secret. So they actually have a YouTube channel where the guy gives something like 20 talks about this project. And it's also...
what's that processor called again?
The what?
What was the name of that project again?
Mill computing.
Oh, right. Yeah.
So if you go to their website, they have a link to all their talks, and so they talk about the instruction format, not in details. And in fact, from one model to the other one, the details can vary. So they have an intermediate code where the program is stored on disk. Then when it's loaded into memory, they translate it to whatever actual processor you have, or something like that. But they've been working on high performance without the energy thing. So their processor is not a sophisticated out of order thing. It goes in different directions. So for example, they don't they separate protection from address translation. So the idea is you map everybody into a single 64-bit address, so you don't have address spaces like in Unix. So that makes porting Unix to their machine a little bit harder, but they have some tricks that help. But they have all these ideas and there's all these talks, so it's a very interesting thing. But it's been going slowly. So far, they only have software simulations. They never got around to implementing an FPGA board, for example. They were looking for somebody to donate $2 million to them so that they could hire somebody to do an FPGA version of their processor. And they've been patching the LLVM compiler, C compiler, to generate code. But they do have the benefits of a tagged architecture, though. So going back to what we were talking about. So they do have protection. So when you read something, it knows if it's a pointer or if it's a integer or a floating point, and it won't allow you to do the wrong thing with the wrong bits. So they have quite a bit of protection there. For example, you can't access your return stack directly. There's a protected means through which you can access it, but you can't just access your return stack and override it, and then when you return, you jump to something else. So it's a very interesting project. I only know one guy, the guy that gives all the talks, which is the guy that wrote the Algol compiler that broke. He looks like Gandalf. He has this really long white hair and this beard that goes almost to the ground or something like that. So he's a very interesting guy. Ivan Goddard, I think is his name. And so I've never seen anybody else from the company, and he's the only one that answers emails and comments on news, whatever groups and so on. So I have no idea who else is in that company, but it's a very interesting project. And my current one is a little bit more like that. So. But I tried to convince the J extension people that the best result we could get would be to fire us to prove that we are not needed. That you shouldn't come into this thinking, oh, we're going to add these neat features. Can we convince people to use that? No. We should try to prove that you don't need that features. And when we fail, then we have an extension. So I don't think they have the risk spirit, because they do want to add stuff. No, they shouldn't want to add it. You should add stuff that, it's really bad if you don't add it. But no, that's not what the various groups want. So. We'll see. I'm a little bit disappointed in the direction. There were a bunch of other stuff. So at one point they were interested in. So that's something that the mill does very well. Zeroing a block of region, of memory, a region of memory. Sorry. So if you have this memory, you've just allocated an object. So in Java or whatever, it's not considered safe if you don't override it all with zeros before you start calling the constructor for that class or whatever. So you should zero out a region. They think that's a critical part of VMs, language VMs, so it would be cool if you had some hardware that could do that. The chair of the group, as his, I think it was his PhD project, he created so he had a design with several RISC-Vs, and then he added a special little processor for garbage collector. So it was a mark and sweep garbage collector. So he wanted to see, because if you implement mark and sweep in software, then you get the pointer, and then you fetch instruction, and then you fetch another instruction, and then you write a pointer or whatever. So his idea was, if he had a dedicated little hardware block, then you just fetch and write pointers, no instructions. So it should be fast. It should use the bus less. So that was their thesis. And it was an interesting project, but the point is, mark and sweep is not a particularly efficient. I mean, we have the copying garbage collectors, generational garbage. Yeah, so some garbage collectors that are so much better.
So the thing where mark and sweep comes back into its own is in parallel collecting.
Yeah.
So, within a thread, yes, you should do copying, but in the shared heap, you should probably use mark and sweep, because then you can have a thread doing the collecting asynchronously with all the other threads. So, yeah, I've been fairly disparaging of mark and sweep for a while too, but I've realized if you have 1,000 processors, you want some of those processors to be able to garbage collect while the other ones are doing work. So
yeah, his idea was instead of having, let's say, 5 RISC-V processors with one running the mark and sweep in software, he had 4 in this tiny little hardware, which has so many fewer transistors. It doesn't have any hardware. It doesn't need to for the mark sweep. So his idea is that it actually, it'd be more efficient. Not only do you avoid fetching the instructions and stuff like that, because in any case, that's probably a simple loop that would go into the instruction cache anyway. It wouldn't be fetched from memory. But my point was that so it only compared the software implementation with the hardware implementation, but maybe replacing it with a different garbage collector. I mean, I understand the point. Actually, the Intel, the first 32 processor from Intel, the 432, did mark and sweep in parallel, just like you said.
Yeah, interesting.
Yeah, it had the 2 bits for the white, gray, and black tagging and stuff like that. So, well, hardware did it in microcode, but yes, you could attach any number of processors and they'd run, and they wouldn't step on each other's toes. So
cool. Did not know that.
it's funny because Intel completely eliminated any reference. So you will never find any material from Intel that mentions that processor. So, the 386, our first 32-bit processor, well, except for the 432 that came 5 years earlier, came in 81 versus 4 years earlier.
Yeah.
But
the 430, the 432 looked like the only hope to carry on the Burroughs legacy.
Yeah, it was an evolution because it was a full capability machine. So it was a step beyond the Burroughs. But I had a bunch of friends that were fans of it, but we were still waiting. It hadn't been released yet.
Yeah.
And then the Berkeley people did some benchmarks where they compared that with the x86 and with their RISC-1 and RISC-2 processors. And they were trying to show off the RISC processors, but actually, when you saw the 432 next to the x86, it was so much worse. So then it says, why will I build a machine with all these 432 processors and then put an x86 on the I/O if the x86 by itself, the 8086 by itself is 10 times faster? But I think people learned the wrong lessons from it. So I know. Sorry.
That often happens. People learn a lesson, but it's often not the right lesson. They have their own prejudices and they see something happening, but don't do enough investigation.
Yeah, for example, the register windows thing again, that people have decided that has been proved to be bad. So Altera created their own little RISC processor called NIOS, N-I-O-S. And the first version had register windows, just like a Spark or RISC-1 or RISC-2 or whatever. And then when they did the NIOS 2, they made it more MIPS-like with a fixed 32 registers, no register window anymore. And I've seen a ton of people point that to me as proof that register windows were a bad idea. And I said, did you see their slides when they introduced the NIOS 2? They said that they eliminated register windows without too much loss of performance. They didn't say they gained performance. They said that they were able to eliminate it without too much loss of performance. That's what Altera said. And people interpreted that as saying, here is proof that it was a bad idea. And so, people sometimes take the wrong lessons. If you see Quora, Hacker News, there's a bunch of forums where people are absolutely sure that object-oriented programming was something that was tried in the 80s and 90s and has failed, and nobody uses it today. I mean, they're completely convinced that that's the world we're living in, a world where object-oriented programming doesn't exist, nobody does it.
So you might be critical of Java and C#, but I'd say they're object-oriented programming.
Yeah. So, You know,
And C++
people,
is even, somewhat, maybe not quite as clean as we'd like, but it's pretty object oriented too. Anyway, I think I need to say goodnight.
Yeah, me too.
okay.
So I will
Thanks
leave you
for
all.
listening to my rants today. So
Yeah, thanks everyone.
Well, it's nice knowing that there's people like you, Giselle, working on the low level stuff. Because I think of like the VM as microcode for the bytecode processor.
Right.
So
well, sometimes I work at an even lower level,
Yeah.
trying to
Exactly.
design the power supply for the thing.
Take care.
Well, take care, everyone. I'm gonna end the call.
Okay.
okay,
Night.
night.